大家好，先前吃完午饭，大家可能有点困的啊。就是说，上午其实我们
little bit sleepy, I guess. This morning we had 3 technical presentations, and in the afternoon we will have 6. That is to say, this afternoon we are going to cover a lot of different topics, and before we start this afternoon, I want to remind you that on your desk there is a feedback form. Please fill it out and return it to us. That is, about this event, this summit, or about DPDK. If you have any suggestions or feedback, please use the feedback form and give your ideas to us. Now, I would like to give the floor to Mr. Lou Yang from TopSec to give us a presentation on DPDK. Hello everyone, I am Lou Yang from TopSec. My company started to work on DPDK very early, as early as 2011. We did some testing at that time, and we noticed that DPDK was a lot more efficient than how we operated our network. But at that time, we had one issue, that was our application was run in the Linux kernel, and I believe most of you did that too. So if we want to realize the potential of DPDK within a short period of time, we may either change to the application layer, which would be very difficult to do, or alternatively, we may migrate the kernel of DPDK to our system, and that was what we did. But now, in recent years, we have migrated our applications to the application layer, but we still did made a lot of changes to DPDK because we had special needs. For example, on the memory management and so on, we modified DPDK to suit our needs. And some of you probably do this, that is, you may use some alternative operating systems that are other than Linux, or maybe your software architecture is very special and it's not applicable to that application layer structure. So for that, it's better for you to move the DPDK core to your application. And when you get better understanding about DPDK, it will be easier for you to make changes to it. That will better integrate your applications in DPDK. So let's review how our work mode was after modifying DPDK. In the right-hand side was the DPDK based. We had CPU, and we used DPDK and polling to operate them. And in the left was the Linux application layer. And there was this message queue in the center. And for example, there are messages that we cannot convert very quickly, so we have to use this queue and put them into the workflow. And in the lower part of this graph, you can see that there is the data plane that drives all the network cards. And there are other hardware devices. We use API-C and use the control plane to control their termination so that they will have minimal interference with the data plane. And this is the workflow or the information flow, data flow. This is a standard DPDK method. And this one here differs from the standard approach in the sense that we give the administration one extra message queue, because sometimes if the administrator wants to send messages, if it has to go through the data plane, there will be one more copy required. That is why we modify DPDK, and here in the network card we have one sending queue for the administrator. And next, about the memory management. There are three parts of it. One is the memory management, the second is the data plane, the third is network hard drive. First, about the memory management. That's something DPDK had a lot of optimization. It has a memo pool. Because we use network devices, and a lot of operation is based on messages. So the using and recycling of the messages are important. So in the memo pool, they optimize the buffer quite a lot. They also have block-free ring, and which make the speed a lot faster than before, and also they support different things like NUMA and so on. In the past we had, and also it supports huge page. Linux is a universal operating system that cannot have special optimization for these messages. It has to cover many different things as an operating system. Linux uses standard approach to manage the memory. For example, its cache and the kernel for its message content and so on. It consumes a lot of the memory, even though it's a little bit like the memory pool in DPDK. However, when you look at the timing, it still has the spin lock and so on. And about DPDK and how it manages the memories. First of all, it has the mapping of the huge page. It has two runs of mapping because it wants to keep the virtual and physical addresses continuous, and then it's locked in the memset. It wants to get large chunks of memory and manage them in a unified way. And in the right-hand side, the upper part is the memo pool. As you can see, with every CPU card, it has a dedicated cache, and every idle object is in a ring, and then it's the heap, and underneath is the map set. That is the structure, the layout. If you want to use the DPDK memory management approach, it's easy. You just provide it with resources. The most basic resources are in the memory set. If you fill it up, it's done. And specifically, here's how we do it. The kernel allocation methods may include kernel lock, get free page, and so on. However, the issue is that it's usually only a few megabytes. Only at the starting point of the kernel, you can get a large chunk of the memory. For example, a few hundred megabytes. It's called reserve boot main node. That is how the system initialized the memory when it's first started. So as you can see, when the kernel is just started, this is the initial management of it, and then that will be replaced by the page list, and after the replacement we can reserve a chunk of the memory. And here it depends on how many net cards and how many other cards you have. Then you can calculate and see how much memory or CPU you may need. And then one important location is that after getting the huge page, it will be saved in the page, and then it will save it there, and then later for heap and for mem pool, it's based on this chunk of memory. And this is our modification to the message. Because when you use specific applications, you will have to modify these things. One special thing we did is like this. The buffer is copied to the management layer. For some messages, it works that way. Most of them are forwarded directly, so sometimes we have to copy it. And we have to put them in special order. And for the shared ones, we put them together so that we can use one copy to initialize all the members. About the memory, it's simple. The key is that we reserve a large chunk of memory for DPDK to manage it. That's all. And about the data plane, it uses the Linux core to achieve that. It's bound to the CPU, and in Linux it's similar. We can use the Linux core thread to do it. Only to change the API to and another method is with a naked core. That is to say, the CPU core is not controlled by Linux. That is a more defined way. I will talk about it later. What is an ideal data plane? I believe it not only should be friendly to CPU, but also it should have minimal shaking. Shaking means that, let's say you have a network device, and when you test it, let's say if we give it 100 G of traffic, it can forward 50 G. Then we say this machine has the forwarding capacity of about 50 G, but if we continue to use instrument to measure it, and we continue to challenge this device with 50 G, can it still forward 50 G? Not necessarily. That is, when you challenge it with 50 G, it may lose a few packets. Like you challenge it for 100 seconds, it loses only dozens of packets. However, for a network device, it doesn't have the rated capacity of 50 G, and then you lower the challenge and it's 30 G in 100 seconds and zero packet loss. That is the real capacity. So where does it lose the 20 G? That is shaking. So the ideal data plane doesn't shake at all. So why does this happen? Because sometimes there may be some interruptions, or there may be some other issues like scheduling of the processes. So we want no interruption, no process scheduling, and light timer. That will be an ideal data plane. And let's look at this. In Linux kernel, there's this feature. That is the isolated CPU start parameters, in which you can set different things. You can isolate a CPU kernel there, and then when Linux is started, these cores don't get any thread tasks. This can eliminate the interruption. And also, when you are verifying the scheduling of the process, you can use PS to read it, to view it, to see all the processes and threads. The CPU ID used currently. So for this LWP, you better show it in the parameter, because about the processes, they don't necessarily have the same ID as the threads using the CPU. So you better view all the thread level IDs so that you can know that There are non-data plane CPU. And another thing is task set command. It can modify the process. The CPU bound to the process. You can look it up to see how this command works, and it will support the kernel. And you can use the kernel threads.
数据面的干扰，以及我们如何去除。
So we have just about how to eliminate the interruption. Next, let's take a look at disrupt. We are most familiar with the timers already because it is used by Linux. It is calculated based on hertz. Every second it happens a couple of hundred times. With Linux application getting better, and particularly the high-performance cameras, all of them are using Linux system. With Linux kernels, it is also trying to eliminate the interruption. When the CPU is idled without any process, maybe it is possible to have the timing break. For the real-time high-performance system, if the CPU currently only have one task, under these circumstances, if you have a timed disruption, that is also not meaningful. This kind of timer can also be eliminated. Next, let's take a look at how to reduce the interruption of data plane. We can turn off IRQ balance service first, and then for the specific timer, we can have it affinited to first, and then we can also take advantage of Dentix idle model of Linux. In this mode, just like we have explained earlier, if you only have one task on the CPU, very similar to DPDK, under these circumstances, you will be able to eliminate the timer, this interruption. Through setting up and through eliminating the localized timer interruption, you can basically guarantee the CPU of a data plane call is not affected by the break. We also have a more ultimate method. You can have the data plane CPU completely demanaged by the Linux. This is the solution we used earlier. It is not as convenient as use Dentix idle. For CPU idle, if you call your own logistics and functions upon booting of the kernel, since Linux supports, it's supportive to a CPU. If it is shut down already, the kernel will no longer manage the CPU. So the CPU is not affected by the plane and not affected by the orchestration either. This CPU will be running natively in your own fetch function. That is also one of the typical environment for data plane. But it is very sophisticated. You need to modify your kernel along with other issues, and the CPU account is also smaller since Linux no longer existing. So there is a lot of things to be changed. We suggest you to use Linux models, so in the future when you upgrade the kernel, it will be more convenient. Lastly, let's take a look at the netcard drives. For DPDK netcard drives, it is one key component. Linux are using API. The Linux has eliminated the receive packet and the transmit packets. Each logic core has its own queues to avoid parallel competition. Each time it is capable of handling more messages. You also need to modify the NAND card register's frequency and timing. For example, you fill in the associated, all of it has to be managed. Let's take a closer look. If you do Linux polling drive in the kernel, it is better that we can have it modified. So how to do that? The management and scheduling can remain the same. In order to ensure stability of the whole system, we only have to make modifications relevant to performance optimization. Firstly, we need to cancel the interruption of the receive and the transmit package. The link state change relevant noticement interruption is still managed by Linux kernel. Among defaulting of NAND card drive, we will need to configure the queue of NAND card receive and sending to the amount of data plane. You will need to have an additional transmitting queue. Under Linux, it is all based on an API, but we need to forget about those. Lastly, to the net device structure, you need to have two additional function pointer. First of all, it is for TX burst, and the other one is for X burst. This pointer will be scheduled by the data plane. Lastly, you need to take record of all of the running devices in order to only pull the running devices. Taking 82599 chips example, when we modify the NAND card drive, besides what we have mentioned above, we have one TX burst, the other X burst. So to receive and send message in the cycle, we also need to optimize and tune the NAND card. We can refer to how we do it during DPDK. If it is a receiver process, hereby we have a tail pointer. We have DD as 1, and all of these are received the message already. The driver needs to receive the message from here. For API, in the standard way, we receive message one by one, have it transformed up layer to do processing. But regarding the pooling, from the tail pointer location, we use EVN to replace it as idle buffer, and then we move the pointer to the front. So from 16 to 32 DPDK, we can handle several of the messages directly. In this way, we will be able to improve the efficiency of receive and transmission of the message. For DPDK, we have done a lot of automation. All of the optimization are based on the reuse of one simple thing in order to improve the performance. For example, the MR pool. Each CPU core, cache, and the ring are based on the matrix. You only need to have 1, 4, or 8. Basically, the costs are similar. So if we have more, we will be able to improve the efficiency of receiving the message. The CPU will also be running in high performance. And to reduce the chance for cache failure, if you only take one header at one time, on one hand, CPU and both net card are writing in the data. If the CPU cache line is 64 bits, one line of descriptor is 64 bits. During the writing, if the other side is reading, it's equal to the CPU is taking away the cache, so the net card performance is sabotaged. That's why it is better to reduce the disruption between the two. So we have the quadrupled times amount in order to reduce the impact. Another optimization is based on RDT. For the RDT register value, it also needs to be modified. The modification on RDT register needs to be in line with the tail. So the net card still has remaining space to store the message. The frequency of this should be as minimal as possible, so it will not disrupt the net card and registers. Based on your application, you can define it to be 4, 8, or any other amount. After one round of polling, we will have the RDT modified and make sure it is quadrupled. Another thing that needs to be set up is around here. For the net card, we have a cache here. The cache is equal and in line to the software. With this cache, you can fully take advantage of PCU idling time to perform and write back. You can define several characteristics and indicators. The first one is PCF, then S/, and then write W/. You can control these parameters. To control the parameters, you will be able to control the timing of writing and reading. For X/, you can design it as 4. So when there are 4, I will do the receive. When write back there are 4, I will start to write back. It is set up based on your application depending on your own needs. If you would like to reduce latency, so you can adjust the read and write / smaller. But of course, you need to do a test, because latency and the throughput, if you have higher throughput, the latency will also go higher. According to your own needs, you can make the right adjustment and choices. When we are doing the modification of the net card drive, on the first hand, we will need to write the function call, and for example, 16, this message account has to be predefined, the timing of modified RDK, and as well as the several parameters of cache. I suggest that you can refer to the slides for your further information. If Linux and DPDK drive support the net card, you can refer to DPDK to make modification. If it is not satisfied, you can do the tuning afterwards. All of the parameters are very known to us already. Then you can have a very detailed tuning. On the other side, we can see the receiver of the message of the packets. It is similar to send out the packets. The principle are still the same. The software will start from the tail to send the packets.
That it changes the TDT, and then here is the net card. There is also that it right back in the cache. So apart from these, we have also touched on the memory management as well as how to create a perfect data plane, as well as how to modify the drives, and also there are other modifications depending on the application. Say for example, from data plane to management plane, we need a pathway, so we believe the DPDK ring is appropriate because it supports the writing and accessing and so on. Also, some of the special messages cannot be forwarded very quickly. That's when we give them to the data plane. We use the standard Linux API. We use the ring to give the message to the Linux core, and then the message is given to the API queue. And then it triggers the forwarding and later processing. Just now, we also mentioned that the management plane needs a sending queue. We use the standard hard start XMIT to send the message. About this, because the net card is no longer controlled by the NDPI, therefore you have to change the way you send the message than in standard Linux, because you will have to recycle you have to collect it. That is, while you send it, you have to collect it. That is different from the standard Linux. Here is what we have done with DPDK and the modification. This is the basic workflow, the process. The key is that there's a puller in the management plane. It has to send and receive messages continuously, and has to use the send and receive packet functions, and releases the messages. If there's a message for the management plane, then it's given to an API, and then the message is sent. This is the final workflow. Now, another thing I want to emphasize is here, the puller. As I said, we were running a naked core. That is to say, there would be no process scheduling or interference. However, there's a third type of interference. That is from the timer. That is to say, the data plane has the pooling. However, we have to do things periodically, such as recycling some resources. When these things are to be done periodically, and they don't want to do it on the data plane because they don't want to trigger any contention, then they may use a puller to do these things from time to time. And then you have to make something like a timer. The timer is actually also done in the puller. About the timer, actually, when we did the testing, we noticed that you will have to minimize the cycling time the timer takes each time, because if you have to do a lot of things, then the timer becomes an interruption to the puller's sending and receiving of messages. That means the data plane is shaking. That is why you may lose a few packets during testing. If you do, you should suspect the timer and see if it's doing too much. If it does, then you should let it do a little bit every time and do it multiple times. And this is from before, from a few years ago. I mean, these were statistics from around year 2012. They are not very relevant now, but let's look at them. In terms of the growth, it was much better than API. And if we look at the other one, which is about the time consumption, this is before and this is after calculation. And the average time of processing one message, this is an API. And the right hand side is this application. It means how much time it takes actually in the application. And the blue bar in the left includes everything like scheduling and sending, receiving, and so on. We optimized it quite a lot already. Compared with Linux and API, we're about 50% better. And if it's standard Linux, this bar will have to move to the right-hand side. And this is after adopting DPDK, as you can see. Apart from the application, the time here is really little. That is to say, if we optimize it in future, we will have to optimize our applications. About DPDK, there is very little potential for further optimization. It's not going to be a lot of progress in future. It still depends on different products, like other experts said this morning. However, for us, we have a lot of treatment to the applications. So we believe optimizing the applications is what we're going to do in the near future. And meanwhile, we want to ensure the linear growth capability of multi-core. If we have an ideal data plane and optimize our data structure and minimize any concurrent interferences, then we can lead to very good linear growth. And let me wrap up, please. On one hand, when moving the DPDK to Linux core, this is an example. Of course, you can still move it to a different place. Like, first of all, you need to allocate a big chunk of memory for DPDK to manage, but do you need to rewrite the memory management? It's up to you. It depends. You can write something like we have written a lot of such modifications. There are all different codes like adding SU to every line or sharing the memory and so on. It's hard for you to use it without changing anything. And then we got an ideal data plane. It's not interfered by scheduling. And we also optimized the standard driver, and we modified it into DPDK model, and so that we can set its parameters inside, like about latency or whatever, to achieve optimal result. After the testing, we found that it's about the same performance as standard DPDK. Okay, this is all for my presentation. Any questions? Hello. I'm from Hudson, and thank you for your presentation, but I think you said that in the past you achieved the kernel DPDK, but then you remove your applications, so you use the user space DPDK. Well, we did a lot of modifications, but the core is like that. So now you put it. You don't have them on the modified DPDK, right? For that project, we wanted to improve the performance within very limited time. If we migrate to the applications to the application layer, it would be too much hassle. So we tried this. However, Using DPDK at the core level, did you have any problems? Why do you still put it back to the user space? Well, because it's hard for debugging. There are many ways to debug the data plane. For Intel and IBM, you can use different tools to measure the leakage of the memory. However, there are some, like, let's say some of your applications may not be suitable for the application plane, and sometimes you may be very reliant on some of the Linux core features. There are different circumstances. This presentation is great, and I have some rather practical question, because I believe different companies may have compromised on DPDK's features. So, any other questions? I'm Li Haifeng from Huawei. Just now you talked about isolate the local timeline cutoff or the isolation of the core. Can we Yeah, every core has the tagline, right? You just mentioned those parameters, those configurations. Well, we minimize the interference ways. I mean, one interference is from outside, like from the hard disk, and also from the timer. But what you were talking about, you were asking for, was about between CPUs, I think. Well, I mean, in the parameters, there is a local timer that prevents the threads from deep hibernation or that time lapse. That one you can get rid of. Let's say on your core you always have only one process. Linux can get rid of that timer, because if your CPU has two cores to run, then you will need scheduling. However, if you only have one process, then there is this feature of Linux. It can make such judgment. It can see that on your CPU you have no processes running, or there's only one process running, and then it will get rid of the timer. But of course, in terms of the data, you should keep at least one. They still need specific time. At least on the CPU, they will have to do the scheduling. But for the CPU, if you have only one thread, one process, then the timer may have little effect on the system. Indeed, by configuring the kernel, we can get rid of the timer. But getting rid of it doesn't mean it reduces power consumption, or that is it gone permanently? Well, the benefit is that when you enter, when you are interrupted or exit, there will be less interference. For example, it may lead to less interruption to the polling. Otherwise, your workflow is interrupted. Okay, for the interest of time, we will stop here. If you have additional questions, please talk to the speakers afterwards. At the end of this summit, I will give the email addresses of all of the presenters to you.